Hello, this is Drik Sarkar, roll number 18 ME33019. Okay, so first we start with the creation of geometry in Design Modeler. So we first select the sketch in XY plane, and then the first step is to draw the circle of radius as mentioned, 240 millimeters, and then we have to trim these sides by drawing these horizontal lines such that the distance between them is 144 millimeter as mentioned, and then we trim the circular regions here, and then the part we have to extrude it, and the extrude material, the height was 6 millimeters. Next we draw this pin, this here, with this circle of diameter 6 millimeters, and and then we cut the material inside the previously extruded material, and the depth of this cut is 5 millimeters where the pin material will be there. And next the shoulder is drawn. So this is the shoulder circular part with diameter 24 millimeters, and this we have to imprint the face on this material. And all these this circle of the pin, this the shoulder circle and the outer circle, they are constrained as concentric. The constraint of this concentric, this is applied. And next, after we create this geometry, this whole thing, next we go to these named selections. So from velocity inlet to bottom face, so velocity inlet is from the side, as we can see this green portion. This is velocity inlet. The pressure outlet is this side. The FSW tool, these three faces, the top face and the bottom face, and the side faces are not named because they will be automatically selected. So this is the part of design modeler in which we create the geometry. Okay, so next we move on to the mesh module. So this is the mesh module. So under mesh, I'll be giving two kinds of sizing. So one is face sizing and another is edge sizing. The face sizing will be of name selection in the FSW tool region. So this part, and the element size, it will be given as 0.00 0.2 millimeters. So it will be 0.002. So we 0.0002 millimeters here. And the growth rate is given as 1.1. And next is the edge sizing. So edge sizing is given in the geometry in the this circle of shoulder region, and here the element size will be of 1 millimeter, so it's 0.001, and the growth rate default will be 1.2. So here I'll be calculating the mesh. Okay, so the mesh has been generated, and you can see that it's a pretty fine mesh in this region. Okay. And this concludes the part of the mesh module. So next we will go to the setup. Okay, so next we go to the setup module. Okay. Okay. So this has opened the setup module, and here we have tetrahedral cells 740,231 and total nodes of 1,11,000 something. Okay, so this is our model, and all this velocity formulation, it will be absolute, the solver will be pressure based and steady state analysis. Okay, so next we go to models. So energy will be on, so energy equation is on, and viscous, this will be laminar, and the viscous setting will be present. Okay. Next we move to materials in the fluid. We This is aluminum alloy AA6061. All these parameters we have to manually input. So like for example, the density, it is 2700 kg per meter cube. The specific heat and thermal conductivity, they are polynomial based, and all these values are taken from the given, all these values are given, and same with the thermal conductivity, all these values. And the viscosity will be non-Newtonian power law, and these values are also taken, like consistency index of this value, the power law index of 0.0421, minimum viscosity 1000, this is 1E6, 298 reference temperature in Kelvin, and activation energy of 1380. Okay, so this aluminum alloy is created, and next we go to the boundary conditions. So here we have first the velocity inlet, and for the velocity inlet, um, okay, so we know that the in meters per second, the welding speed is 0.00133 meters per second. This is in the absolute reference frame, this value, and since this in the x direction, it is in the x direction, this x component of flow is 1 and all the others are 0. This is the velocity inlet, and next is the pressure outlet. Okay. In velocity inlet, there was temperature as well, 300 Kelvin. And the pressure outlet, we have this gauge pressure is 0, and the reduction vectors, this will be same as well, and this will be 100, and in thermal this will be 300 Kelvin of backflow temperature. Even there will be no backflow because it's flowing. So this flows, and next we have the valves. So let's start with this FSW tool. This FSW tool, there will be rotating boundary condition. Mm, so here we have a no slip condition. This is a moving wall, and the motion is with respect to absolute motion, and this is a rotation boundary condition. This is rotate about z axis, and the speed in rads per second is 74.351. So this value we have got by 710, since it is 710 rpm. So from rpm, 710 into 2 into pi 60, so we get 74.351. So 74.351, yes, 74.351. So this is done, and next let's go to top face. So the top face is also a moving wall. Motion is absolute, so same as the welding speed is 0.00133 meters per second. Direction is 1. This is translational motion and no slip condition. In thermal, we will have convection with heat transfer coefficient of 30 and free stream temperature 300. And in the bottom face, we'll have It is a moving wall, absolute speed 0.00133 meters per second, translational. The direction will be in x direction and no slip condition. And in thermal, there will be convection, and this is a very high value because we'll have convection here a lot. 10,000 watts per meter square Kelvin, free stream temperature 300, and the wall solid. Wall solid is basically the one which we have not, where the name selection were not done. So these side walls. So this is also moving wall with absolute speed of this one. It's translational and no slip condition, and thermal will be a less value of heat transfer coefficient of 30, free stream temperature 300. So these were the boundary conditions. Okay. After the boundary conditions, we go to the method of formulation. So methods, these will be all the default values, the default conditions. So next we have the report definition. So these report definitions I have already created before. So these are the four. So I'll just give one of the examples here. So for weld force, this will be on the zone will be FSW tool. This report type will be drag force, and the vector for this particular force is in 100 direction. So we'll all plot this report file, report plot, and create output parameters. So similarly, so this was for weld force, this was 100. For example, for thrust force, this will be 001. So because the vector for thrust force is the force vector is along the z direction, so FSW total drag force and so on. So all these four values will as report definitions. Okay, next we initialize we'll do hybrid initialization and initialize. It's taking a bit of time. Okay, so the hybrid initialization has been reached, and next we'll run the calculation. So I've given number of iterations as 1000, let's increase it to 2000. These are okay, and next I'll calculate. This will take a bit of time, so I'll be pausing the video and I'll be resuming after the results. Okay, so we see that the calculation is complete and it is completed just now. So at 3:14 p.m. So it started at 2:22 and it ends at 3:14. So it has taken about um, 54 minutes. It was around. So it has taken about 52 minutes to solve with the element size of 0.2 millimeters. And here we can see the scale residuals, the plots of torque. So all these values they have converged: the torque, thrust force, lateral force, and weld force. So if I want to know the values of these, so let's see the weld force. So for weld force, it is 17.71 Newton. Next is the lateral force. So lateral force is 7.8 Newton. The thrust force is 6.569 newtons, and the torque is in Newton meter. It is minus 37.92. Okay. Uh, okay. So next we have to plot contour plots for temperature and viscosity in weld cross section. So this is the cross section. Um, so this is the contour for temperature, the static temperature, and in this plane. So I'll compute and save display. Use this. We'll just zoom in on here. So you can see This maximum is the legend for the plot. So you see here it is maximum, it is going to so the maximum is going to 592 Kelvin, and here it is going to 592 Kelvins maximum temperature. And for viscosity, here, so for viscosity, this consists of properties, molecular viscosity in this plane 6. So compute and display. So this is the molecular viscosity. So so if I zoom in this region, you can see this. So the maximum molecular viscosity is going as 10 power 6 as we have inputted, and this minimum it is going, okay, it's not here. So yeah, this is the minimum value. So you can see this plot in the weld section. We can also plot the temperature in the top surface. So the temperature in the top surface. You can also add this. So yeah, this is the surface in the pin in the middle. Okay, and the iterations that took it to converge is 418. And yeah, okay, now to study the effect of mesh size on the results of the simulation. Uh, I have calculated using three different types of elements, so element size near the pin zone. So the first one, which I have showed in the various all the details which I've shown, is these zero point 0.2 millimeters, and these two extra I have simulated. So the first one was zero point 0.2 millimeters, the second was is zero point 0.3 millimeters, and the third one is zero point 0.5 millimeters. So I simulated all of them and took all the values, checked all the values, and these are my results. So for the zero point 0.5 millimeter one, so the number of cells, this is 131,000, faces is 270,000, and nodes 25,000. So the number of iterations that took to converge in this one is 407, and the time it took for convergence is 7 minutes. And these are the output parameters: torque, thrust force, lateral and well force. And in the stir zone and the weld zone, the peak temperature was 590.632. The second one is the zero point 0.3 millimeter one, and the number of cells will definitely they increase. The cells number of faces and nodes will definitely increase, and the number of iterations that took to converge was 419, and the time it took was 20 minutes, around approximately 20 minutes. And these are these output parameter, these values of torque, thrust force, lateral force, and angular force, and peak temperature was found to be 591.8235. And the next one was this one, the zero point 0.2 millimeters one. So through this we can see, and the time taken was 52 minutes, and the number of iterations was 418. These are the cells, faces, and nodes. So we could see that the torque was almost converged to the like the new the first integer. It was converged, so minus 37. So in the first decimal point, first decimal, it was still not converged to the first decimal. So and the peak temperature, this was also around like approximately converged around 590. So yeah, these are the results. And lastly, I would also like to say few of the interesting things that I've learned through this. So the concepts of dependency on mesh size, this is kind of new to me. This was kind of new to me. and various processes of the report defining the report definitions and drawing the contour plots, plotting the contours and so on. And lastly, I would like to thank you, Professor Vikram Chachela, for this beautiful assignment that I could do. It was very interesting in doing it. And thank you, sir. Lastly, I would like to repeat my name and roll number. Drik Sarkar, 18 ME 30 18 ME 33019. Thank you.